Hello everyone, in this video we start the chapter 14. First we will cover the section 14.1. Generally in the chapter 14 we generalize the structure of one-dimensional calculus to multi-dimensional calculus. Namely, we will see functions of two variables or more variables, the derivative of multivariable functions, and double integral, and so on. Namely, we generalize this one-dimensional calculus that we have learned in calculus 1 to multivariable calculus. First of all, of course, we will define multivariable functions. We know already functions of one variable, which is defined as y is equal to f of x, like this. So first we will see what is the definition of a function f of two variables. So this is a rule which is very similar. Actually, this is the generalization of the definition of one variable functions of one variable. So a function of two variables is a rule that assigns to each ordered pair of real numbers x, y in a set D, which is a subset of R square, since we have an ordered pair like xy instead of x. So it assigns a unique real number denoted by f of xy. The set D is called the domain of f, and its range is the set of values that f takes on, that is the set given here. So we can understand that when we want to define a function of two variables, so we take a set such that the function is defined here, and this will be a subset of R square. So R square, it goes to the set of real numbers. So since the set D is a subset of R square, so we have two variables. The first one is the first component, which is x. The second variable is the second component of the point in the set D, which is the subset of R square. So by giving any value for x and y, we get a number denoted by f of xy. So it is also written as f of xy is equal to z, like functions of one variable. Normally functions of one variable is defined as a set, let's say E, which is a subset of real number. It goes to the set of real numbers. So we have one variable, from calculus 1. So the value of f at x is denoted by f of x, generally, theoretically. And also we say this is equal to y. Here x is the independent variable, y is the dependent variable. But for functions of two variables, we have two independent variables, which are x and y, and the dependent variable now is z. So we have two independent variables, two unknowns for functions of two variables, and the dependent variable instead of y will be z for functions of two variables. And also the difference between the domains of these functions is that the first one is a subset of R square, since we take two numbers, and the domain of the second one is the subset of the set of real numbers, since we have just one independent variable. Okay, this is the generalization of functions of one variable to functions of two variables. We consider the same structure, but just we increase the number of variables, which is 2. So as I said, we write z for the value of f xy to make explicit the value taken on by f at the general point. The variables x and y are independent variables and z is the dependent variable. A function of two variables is just a function whose domain is a subset of R squared and whose range is a subset of R. Okay? Namely, we can describe the domain of f for functions of two variables in two-dimensional coordinate system. But the domain of functions of one variable is described in R. Like, for example, f of x is equal to square root of x. What is the domain of square root of x? You know, x cannot be negative but can be 0 and positive numbers. Therefore, the domain of f of x, which is defined as square root of x, you know, is equal to the set from including 0, therefore we have closed interval, to plus infinity. We include all positive values. Also we have the number 0. Square root of 0 is equal to 0. So this is the domain of f, which is a function of one variable. You see, just we have x, but for functions of two variables, the domain will be a region in two-dimensional coordinate system. For example, also you see this is a subset of the set of real numbers. Okay. For example, let's find the value of f at 3, 2. You see we have two values since we have two independent variables f of xy, and sketch the domain, namely describe the domain, the region which is the domain of the function in two-dimensional coordinate system. So now we will find first the value of f at the number 3, 2. Okay, the number 3, 2 is a point in the domain of f. Now we will find the domain of f, and you will see the 3, 2 is in its domain. So first let's learn how we can find the value of f for functions of two variables by looking at this example, finding also its value at 3, 2. So this is the same as the functions of one variable, just we write the numbers for the independent variables in the definition of f. So the first number is corresponding to the variable x, since x is written first in this order, and 2 is written for y because the second variable is y in this order. Also you can write yx, but here the order is important to determine the points such that they are corresponding to the necessary independent variables. So the number 3 is written for x, so we have here 3 plus 2 becomes 5 plus 1 becomes square root of 6, and when we write 3 for x we get 2. So the value of f at this point is square root of 6 over 2. For the second one, similarly, for x we write 3, for y we write 2. So we have 4 minus 3 in the parentheses here. We have logarithmic function. 4 minus 3 becomes 1. ln 1, you know, is equal to 0. 0 times 3 becomes 0. Namely, f of 3, 2 for the second one is equal to 0, which is corresponding to the variable z, which is the dependent variable because it is dependent the variables x and y. When we change the x and y when we write another number, so the variable z will be also will change. And for the first one, f of 3 2 is equal to square root of 6 over 2. Okay, so we find the values of f of two variables by writing just the numbers for the corresponding independent variables. So how can we find the domain of these functions? You see we have two variables, so we will look at the definitions of the functions to determine the domains of them, like the functions of one variable. To find the domain of f of x, which is defined square root of x, we use the properties of the some special elementary functions like square root of x, or logarithmic functions, or rational functions, and so on, like polynomials and so on. So when we look at the definition here, to define f, the denominator should not be 0. So from here, first we understand that x minus 1 should not be equal to 0, which means let's write here again, f of xy is defined as square root of x plus y plus 1 over x minus 1. So from here we understand that x minus 1 is not equal to 0. Okay, so we have here x is not equal to 1 always. Okay, so we don't take the points, all points actually, such that the first component is 1, because x will not be always 1 for all points in the domain of this function. And when we look at the numerator here, we have the root function. Root functions are defined if the degree is even number. You see the degree is 2 here actually. Therefore the term inside the root function should be a non-negative number. Therefore we write x plus y plus 1 is bigger than or equal to 0. Okay, so this is the first known identity. So this is the second one. So to determine exactly the region, actually the domain of f, so we will consider first this inequality as an equality to describe the region, because we have also here the equality. So we write x plus y plus 1 is equal to 0. So from here x plus y is equal to minus 1. This is actually a line in two-dimensional coordinate system. And if you remember, it is its graph is obtained by writing the intercept points. X-intercept can be obtained by writing 0 for y. When we write 0 for y, we get minus 1 for x. And similarly, writing 0 for x, we get minus 1 for y. Therefore, the graph will be like this. For this line, okay. And the second one says that take all positive or all the points bigger than actually this line, okay, bigger than this line. Therefore we take all values, all points above this line. Also we should not take all the points for such that the first component is equal to 1. So if we consider This is actually another line in two-dimensional coordinate system, x is equal to 1. So we don't take all points on this line. X is equal to 1. X is equal to namely we don't take all points on this line, and all other points in this region will consist of the domain of f. Namely, the domain of f defined here as the region located here except x is equal to 1. Okay, this is the domain of f. Using the properties of the elementary functions, this is actually a division function. In the numerator we have the root function, which is an elementary function, and x minus 1 is another function, which is a linear function, and so on. Similarly, you can find easily the domain of the second one. Here we have logarithmic function. You know, logarithmic functions are defined for positive values. Therefore, we should write y square minus x should be bigger than 0, which means y square should be bigger than x. And when we sketch by considering this is an equality, namely we have x is equal to y square, and its graph will be like this, you know, x is equal to y square. This is the graph of x is equal to y square, and we should take y square minus 1x is bigger than 0, which means we take all the points which are located the outside of the x is equal to y square, you see. Okay, so the expression, and this is the explicit definition of the domain of f. This is actually the theoretical definition. This is the geometrical definition of the domain of f written here. So the theoretical definition, as I said, will be we have two information here. X should not be equal to 1, and x plus y plus 1 should be bigger than or equal to 0. If we have these conditions for every ordered pair of numbers, two numbers written here x, y, so this is in the domain of f defined here. Similarly, we have one condition for the second function for determining the domain of this function, which is written as x is less than y square, or y square is bigger than x. Similarly, let's find the domain and range of the function g of xy defined as square root of 9 minus x square minus y square. Similarly, we have also root function here. So, you know, root functions are defined for non-negative numbers, which means 9 minus x square minus y square should be bigger than or equal to 0. This is the theoretical definition of the domain. Or writing x square and y square to the right side, we have x square plus y square is less than or equal to 9. Okay. Actually, if we consider to determine the domain of this function in two-dimensional coordinate system, we consider first the equality. X square plus y square is equal to 9, you know, is a circle, you see, with radius 3. And since we have x square plus y square is less than 9, which means when we take any numbers for x and y, so the term x squared plus y squared has to be less than 9, which means we take all the points inside the circle. For example, when we take 4, 0, which is the outside of the circle, so we don't have this condition because we have 16 plus 0, which is equal to 16 less than 9, which is not possible. This is impossible situation. Therefore, we cannot take this point, which means we cannot take all the points outside of the circle. Therefore, we take all the points which are in the circle. And we have a special name for this. This is called a disk with center, origin, and radius 3. Namely, the domain of function g is a disk with the center, origin, and radius 3. You can see. And the range of g is z, which is equal to square root of 9 minus x squared minus y squared, and you know this cannot be negative. Therefore, z is always bigger than or equal to 0. And also we know 9 minus x squared minus y squared is always less than or equal to 9. Okay, because x squared is always positive number, y squared is always positive number, and we have always negative number for minus x squared, and we have always negative number for minus y squared. 9 minus negative value becomes a number less than 9. Therefore, when we take square root of both sides of this inequality, we obtain square root of 9 minus x squared minus y squared is less than or equal to 3. Okay. Therefore, we know z is always bigger than or equal to 0. Z is bigger than or equal to 0. And we know it is also less than or equal to 3. So when we write any number for x and y every time, we obtain a number between 0 and 3, which means the range is between 0 and 3, which is the closest interval from 0 to 3. So this function actually is defined from the disk. Actually, f is defined from this disk to closed interval from 0 to 3. When we take any point in this disk, f of xy, for example, will be between 0 and 3. Okay. And if f is a function of two variables with domain D, then the graph of f is the set of all points x, y, z in R cube such that z is equal to f of xy and xy is in the domain of f. So just as the graph of a function f of one variable is a curve with equation y is equal to f of x, so the graph of a function of two variables is a surface with equation z is equal to f of xy. Do we say it is a surface? Because we have actually three variables for functions of two variables. The first two are independent variables. The last one is the dependent variable, which is obtained by f of xy. Z is actually f of xy, and any point in the graph of functions of two variables can be written generally as x, y, f of xy. Instead of z, we write f of xy, like the functions of one variable. You know, functions of one variable can be seen in two-dimensional coordinate system. It is stated in two-dimensional coordinate system geometrically a curve, generally like this. Okay. and any point here is written as x f of x. Okay, for functions of one variable, you know from calculus 1, y is equal to f of x. In the graph of this function is determined in two-dimensional, be careful, two-dimensional coordinate system, since we have two different numbers, x f of x, x f of x. Similarly, for functions of two variables, we have three actually variables, z, x and y. Therefore, it is corresponding to a point in three-dimensional coordinate system, x, y, z. Therefore, this is actually the generalization of functions of one variable to functions of two variables, x f of x, xy f of xy, since we have two independent variables here, but here we have just one variable. Therefore, the graph of this function states a curve in two-dimensional coordinate system, but the graph of this function states a surface like this. You see, this is not a curve, this is a surface like the sphere, like the cylinder, like the ellipsoid, and so on. We have actually a thing such that it has a volume. Okay, can have a volume. So we can visualize the graph of functions of two variables lying directly above or below its domain D in the xy plane. You know, when we take the projection from calculus 1, when we take the projection of the graph of functions of one variable, the functions defined y is equal to f of x, we get the domain of f, or the closed interval. The domain of this function will be, if you say this is the number a, this is the number b, which are the endpoints. So we write a, b. Okay, this is the domain of this function, and the domain of functions of two variables, if we know its graph, which is a surface in three-dimensional coordinate system. So when we take the projection onto the xy plane, and similarly like this, similarly the functions of one variable, when we take the projection of the curve onto the x-axis, we get the domain of y is equal to f of x. Similarly, when we take the projection of the surface onto the xy plane, we get the domain of functions of two variables, like the disk, like this region. This is actually the projection of the graph of f in onto the xy plane. Okay, this is the visualization of this function in the xy plane graphically. Similarly, when we consider the general case of the functions of two variables, f of xy, so the projection of the graph will be the domain of f in the xy plane. So sketch the graph of the function f of xy defined as 6 minus 3x minus 2y. And let's also find the value of f at the point minus 1, 2, for example, to understand very well functions of two variables. We write minus 1 for x. Minus 1 is corresponding to the first variable, 2 is corresponding to the second one. So when we write minus 1, we get plus 3, and 6 plus 3 becomes 9. 9 minus 2 times 2, 4. 9 minus 4 is equal to 5. So to sketch the graph of this function, this is actually a linear function in two variables, calculus. The graph of f has the equation by writing the third variable. Instead of f of xy, we write z. Z is equal to 6 minus 3x minus 2y, and when we write all variables in one side of this equality, we get 3x plus 2y plus z is equal to 6, which represents a plane. If you remember, the normal vector of this plane has the components 3 to 1, and d is equal to 6, for example, and so on. So to graph the plane, we first find the intercept points. How can we find the intercept points? Writing the number 0 for two variables like xy by taking two of them and writing 0, we get the intercept points for each variable. For example, when we write 0 for y and z, we get 3x is equal to 6. 3x is equal to 6, so x becomes 2. So this is the first intercept point, which is on the x-axis, since we write 0 for the other variables. 2, 0, 0. Similarly, writing 0 for x and z, we get 2y is equal to 6, y is equal to 3. So the second intercept point is located on the y-axis, and writing 0 for x and y, z is equal to 6. And by combining them, we obtain actually the direction of the plane will be like this. Okay, it is passing through the points 2, 0, 0, 0, 3, 0, and 0, 0, 6. So you see, this is not perpendicular to the xy plane, since it cuts the z-axis at the point 0, 0, 6. So if you remember, this represents a plane. Okay, and f of xy is equal to ax plus by plus c is called a linear function in two variables calculus, and its graph is a plane in three-dimensional coordinate system. When we have this structure in any example or any concept, we understand directly this represents a plane graphically in three-dimensional coordinate system. Actually, this is the generalization of the function y is equal to f of x, if you remember from calculus 1, is equal to ax plus b. This represents a line, if you remember, y is equal to ax plus b, such that a is the slope and b is the y-intercept point. Actually, another form can be written as y is equal to mx plus n. M is the slope of this line, and n is the y-intercept point. Similarly, the generalization of this function is called a linear function in two variables calculus, and this becomes a plane in R cube. The generalization of the line to three-dimensional coordinate system is a plane. Okay, so sketch the graph of g of xy. We found its domain, which is a disk, you see, of this function. So to sketch the graph, we do some calculations for the definition of the function to see a known equation for the function. So instead of g of xy, we write the third variable z, and we square both sides of this equation, so we obtain z square is 9 minus x square minus y square, and from here we get x square plus y square plus z square is equal to 9, which we recognize as an equation of the sphere with center the origin and radius 3. This is actually a simple sphere with radius 3. But when we look at carefully the definition of the function, you see we have always non-negative values, which means we don't take the negative side of the sphere. Therefore, we take the semisphere with the positive side. Since z is not equal, bigger than or equal to 0. So the graph of G is just the top half of this sphere. This is the semisphere with the positive side, since because of the definition. Okay, and intercept points similarly can be found by writing 0 for two of them. When we write 0 for y and z, we get x squared is equal to 9. Since we consider the positive case of the sphere, so x becomes 3, 3, 0, 0. Similarly, 0, 0, 3 and 0, 3, 0. So this is the graph of this function. And when we take the projection of this surface onto the xy plane, you see we obtain a disk. Okay, we obtain a disk. Namely, we take all the points because we cover all the top half of the sphere. The projection is onto the xy plane is the domain of this function with radius 3. You see, you can understand by looking at the intercept points, the radius of the disk will be 3. Similarly, you can find the domain and range and sketch the graph of edge of xy, namely z is equal to for x squared plus y squared. You know, if you remember the table in the section 12.6 for some quadratic surfaces, this represents an elliptic paraboloid, if you remember. Or if you don't remember, you can describe the graph by finding the horizontal and vertical traces. Horizontal traces, you know, can be found by writing any constant, any number for the variable z, which means actually we cut the surface with the horizontal plane, which is parallel to the xy plane. Therefore, z should be a constant. Generally, we write z is equal to k to find the horizontal traces. When we write k for z, we get actually an ellipse, an equation of the ellipse. Therefore, horizontal traces are ellipses and vertical traces are parabolas. And by writing any constant for x or y, namely we cut the surface with vertical plane to find horizontal traces, or like this. This is the first type, this is the second type. First type can be obtained by writing any constant for y, and this one can be obtained by writing any number for the variable x. So when we write any number for x, for example 0, we get z is equal to y squared. So you know this is a parabola. Therefore, when we write 0 for y, we get z is equal to 4x squared, which is another type of the parabola. Therefore, the vertical traces are parabolas like this, and horizontal traces are ellipses. When we cut this surface with horizontal plane, we obtain an ellipse, okay, like this. And when we cut vertically like this, we get a parabola, which is the intersection of the vertical plane and surface. And we can understand here this is an elliptic paraboloid. So another method for visualizing functions is a counter map on which points of constant elevation are joined to form counter curves or level curves. So if we cannot sketch easily the graph of a function of two variables, so we can visualize these functions graphically just by finding its level curves. Okay, the level curves of a function of two variables are the curves with equations f of xy is equal to k, where k is a constant in the range of f. Okay, namely for the variable z we write a constant. Actually, just we find the horizontal traces. Level curves actually the horizontal traces of the surface. And to determine exactly the level curves in two-dimensional coordinate system, we take the projection of them onto the xy plane like this. But after finding the horizontal traces, you see generally the general concept here, they are ellipses, you see, or circles. So we take the projection of them onto the xy plane and we obtain the level curves or counter map of the function of two variables. This is the counter map of the function of two variables, and these are the level curves of this function can be obtained by writing a constant for the variable z. K is equal to f of xy, which means actually in this equation we have just two variables, which means this becomes a curve. This becomes actually a closed form functions of one variable, if you remember calculus 1. So this is another visualization of functions of two variables. This is the counter map for some function. So we can estimate some values of f by using this counter map. For example, f of 1.3 can be found by finding the number, the point 13 here. So when we look at the levels of this counter map, it is between 70 and 80. So this is corresponding to a value between 70 and 80 for the image under f for this point. Therefore, we can estimate, since it is closer than the level curve 80, it is closer the level curve 70, which is closer than the 80. Therefore, we can write it is approximately equal to 73. Similarly, after finding the point for 5, this one, so it is between 50 and 60. So it is close the level curve 60, so a little bit. So we can write approximately it is equal to 56 and so on. Actually, also you can say, for example, in your opinion it is 56.5 and so on, but we know definitely it is between 50 and 60. So sketch the level curves of the function, which we know its graph. This is a plane for the values k, minus 6, 0, 6 and 12. Namely, we have just two variables in here. When write level curves generally can be written as k is equal to 6 minus 3x minus 2y. And for example, when write minus 6 here, Actually we have just two variables here, therefore it represents a line in two-dimensional coordinate system. So when write -x here, we get, and writing the variables into the left side, so we get 3x plus 2y is equal to 12. Instead of k we write -6, and we have already plus 6 in this side, therefore we have 12 for the right hand side. So after finding the intercept points, for example, when write 0 for x, we get y is equal to 6, therefore it is passing through the number 6 in the y-axis, and when write 0 for y, so we get 4 for x, so it is passing through the number 4 on the x-axis. Similarly, when write 0 for k, we obtain 3x plus 2y is equal to 6. When write 0 for y, we get x is equal to 2. And similarly, when write 6 for k, we obtain 3x. 3x is equal to minus 2y, which is a line passing through the origin, you know. And when write 12, we obtain 3x plus 2y plus 6 will be this line, and so on. You see, all level curves are parallel to each other, and they are lines in two-dimensional coordinate system. So by combining them in the three-dimensional coordinate system, you will see this is a plane. And similarly, you know, the graph of this function, it is the top half of the sphere with radius 3 and center the origin. So when write a constant for the variable z, we get x squared plus y squared is equal to writing the variable k into the left hand side, and writing other variables to the left hand side, we get x squared plus y squared is equal to 9 minus k squared. Okay, this is a family of concentric circles with center 0, 0 and radius 9 square root of 9 minus k squared. This is a circle, you know, this is a circle. Name the level curves are circles for this function, and you can see also from the graph when we cut this sphere with horizontal planes, you know, level curves are actually the horizontal traces, we obtain a circle. Okay, therefore level curves have to be circles, and theoretically we prove they are circles also. And when we write any sample values for k, you can see, for example, when we write 0, we get x squared plus y squared is equal to 9. This is the biggest one in here. And when we write 1, we get x squared plus y squared is equal to 80. So the radius becomes square root of 80, which is the second bigger circle, this one. When write 2, we get 5, the third one. When write 3 here, we get 9 minus 9 is equal to 0. So we have x squared plus y squared is equal to 0. So we have the only point satisfying this equality, which is the origin. Therefore, just we have a point for the last one. Okay, this is just a point. Actually, this is the projection of the sphere for the top point. Okay, for the top point. And similarly, you can see the level curves of this function. When we write z here, we obtain, when we write any constant here for z, we get an equation of ellipse and you can see the level curve similarly, and you can see the projection of the horizontal traces onto the xy plane, which consists of the counter map of this surface. This is the counter map of this surface. For example, this is important for geology. A function of, also we can define more functions of more variables. A function of 3 variables is a rule that assigns to each order a triple x, y, z in the domain which is a subset of R3, a unique real number denoted by f, x, y, z. So here we have 3 independent variables. For instance, the temperature T at a point on the surface of the Earth depends on the longitude, latitude and of the point and on the time. Namely, the first 2 variables determines the location, and the last one determines the time. And by combining them, we obtain the temperature in this location on the surface of the Earth. Okay, namely we have a lot of applications for multivariable functions in applied science. This is very important concept for engineers. Functions of 2 variables, functions of more variables, and the multivariable calculus. So find the domain of f. f x, y, z is defined as ln z minus y plus xy times sine z. You know, logarithmic functions are defined for non-negative positive values. Therefore, z minus y has to be bigger than 0. So the domain of f, and we don't have any constraint for the trigonometric function sine. Therefore, the theoretical statement for the domain of f of 3 variables, actually we have 4 variables, writing t is equal to f of x, y, z. This is more generalization of the definition of functions to more variables. So we have the only condition, z has to be bigger than y. For example, 0, 1, 2 is in the domain of D, because z is bigger than the third component is bigger than the second one. But for example, this point minus pi, minus 2, minus 3 is not in the domain, because the third variable is less than the second variable, which means this point does not satisfy the condition written here. Therefore, this is not in the domain of this function, and we don't have any constraint for the first component. Therefore, we can write any arbitrary number for the variable x, and we can understand the domain of f given in this example easily, theoretically, by using the only condition obtained from the definition. And it is very difficult to visualize a function f of 3 variables by its graph, since that would lie in a 4-dimensional space. Since we have 4 variables, so the graph of this function is located in a 4-dimensional space, r to the 4. So our brain cannot understand the 4-dimensional space. Therefore, we cannot visualize the graph of functions of 3 variables. So we can also actually, to understand visually the graph of functions of three variables, we will benefit from the level curves or the counter map of this function in three-dimensional coordinate system. The most general case for definition of functions of more variables can be considered in this form. A function of n variables, this is the most general case for definition of functions to multidimensional calculus, is a rule that assigns a number z to n tuple x1, x2, x3, x4, and so on. We have n independent variable and one dependent variable. It is dependent depending on the variables x1, x2, x3, and so on. So we denote by Rn the set of all such n tuples like this. Okay. Actually, the function is defined from Rn to R. We have n independent variables, namely x1, x2, blah blah blah, xn. So it assigns a number. Let's write here, or let's create another page. So f is defined from Rn to R, x1, x2, blah blah, xn, f of x1, x2, is equal to some variable, let's say t. T is the dependent variable, x1, x2, blah blah, xn. We have n independent variables. For example, we can use this function in some applications. For example, if a company uses n different ingredients in making a food product, CI is the cost per unit of the ith ingredient, and XI units of the ith ingredient are used, then the total cost will be the addition of them of the ingredients is a function of the variables, and x1, x2, blah blah, xn are the units of the ingredients, and ci are the cost of these ingredients. So total cost will be the addition of them. So the function f is a real valued function whose domain is a subset of Rn, and sometimes we will use a vector notation to write such functions more compactly if we consider the independent variables as the components of the vector x, x1, x2, blah blah, xn. So we often write f of x in place of f of x1, x2, xn to get an easy expression for functions of more variables. You will see also in the second year in the course linear algebra mostly. So with this notation we can rewrite the function defined in this equation as c times x, where c has the components c1, c2, cn. If you remember the definition of the inner product, it is equal to actually this one. So an easy expression of this definition can be obtained by the definition of the inner product easily. Actually, it is similar to the definition of one variable functions. Just we have one variable x, and this is equal to c times x. You see, this is more easy expression for this function instead of n independent variables. So it seems that we have just one independent variable. Okay, that's it. Thank you very much for your